right. Okay. So you can find the codes from my group here if you go to this GitHub. And Xtag is the unsupervised learning I talked about yesterday. If you go to that GitHub page, you can find the code, also tutorial, notebook, Jupyter Notebook, together with sample data so that you can play around with data. Something that I'm going to talk about today, second half of the talk, Hartree-Fock, doing Hartree-Fock using language model. You can also find code in this site. There is also code for the first part of today's talk, which is somewhere below. All right. So I want to talk about two papers today. Well, 2+ papers. Both are trying to use machine learning tools to make more sense out of data, but data not in the form of experimentally obtained raw data, but data that's been curated. So first, I want to talk about trying to gain insight from labeled data that's been curated by experts, and that is sort of a way of trying to see whether machine can learn what an expert would learn by mining thoughtfully curated data and maybe go beyond it. So the first example that we studied in this paper was that of topological semi-metal. And the choice here was mostly because this is a very new type of adventure. It's something that has not been done before. And we wanted to pick something that we have a way of benchmarking. So the benchmarking was relying on Leslie and her group's understanding and the intuition that they developed. And this was, again, collaboration with my collaborator, Andrew, and his student, and my student, Yanjun, and former postdoc, Krishna. So what are we trying to do? So material scientists go through many trial and error, as I understand it. And as they go through trial and error, renowned material scientists that we hear about, as somebody who's made a major impact, usually they have this intuition. You ask them some question, do you think blah would work? They would say things like, oh, my gut feeling says, it's not going to work, or it's going to work. So what is that gut feeling? That gut feeling is something that they develop through their lifetime of purposeful experimentation. It's the empirical learning that they have internalized. But what they have internalized may not necessarily be something that can be spelled out in the form of instruction that can be passed along. I think of it a little bit like, when I was little, I asked my mother how to make certain dish. And she charged me with feeding my family because I'm a girl, although my father was at home, was staying with us, but she was going away. She charged me with the task of feeding the family. And she told me, you make this bulgogi. It's a meat dish. So I asked her, so how do I make this thing? And she said, well, you put the right amount of soy sauce and the right amount of sugar, right amount of garlic. And, there was obviously right amount in her mind, which is very obvious to her. And it was also obvious to most of her friends who's been doing this for many years. Totally not obvious to me, right? So that's an example of something that people have developed through experience. When it is not articulated and formulated, it is not transferable. So what is better? What is better would have been for her to say 250 milligram of this or milliliter of this and 400 milliliter of that. Then I would have been able to repeat. So the question is, if we give machines the experience expert went through in going through a collection of data from a particular perspective, can machine give us sort of an articulation? Perhaps that will help us see what is logic, and perhaps it will help us go beyond what was immediately reasonable by a single expert. So trying to go from trying to find reason, logic, pattern, organization from observations is not a new desire. Perhaps somebody who was most successful early success in that effort would have been Mendeleev. Before the structure of atom was understood, before quantum mechanics was understood, based on observations, he came up with the idea of tabulating different elemental materials. And a lot of properties of elemental materials can be boiled down to their atomistic properties. Hence, we learn the periodic table. But from periodic table and what is the meaning of the column versus row, we can infer a lot about elemental materials. But once you start to have non-elemental materials, it becomes very hard. You cannot just combine property of one element and another element to understand the property of the material consisting of the two elements. Chemists, I learned a lot of chemistry working with Leslie, much more than from my chemistry teacher in high school, who just told us to memorize the periodic table. And it was hard for me to blindly memorize. But what I've learned working with Leslie is that chemists really, the periodic table is very close to their heart. They really think about their elements. They start from elements and atoms. Condensed matter physicists, because of the success of the band theory, often like to start from the band structure. It's different basis, different starting points. The benefit of thinking about atomistic properties, as chemists think, it's so easier to think about how you build them if you know how to combine them. So there is benefit in trying to have different perspectives, not just the band structure perspective, but also from atomistic properties. And what we wanted to do was to see if we can develop the intuition that Leslie developed by giving the same experience to machines. In order to go through this adventure, we needed to have reliable data, and we needed to have benchmarking insight, which came from what Leslie was able to reason. So what we thought we would do is we'll go through these square net materials. These are a family of square net compounds. They have the name because they all have this structure where there is a square net. Maybe there's one here or multiple here, but they are separated by other atoms. So what Leslie's sort of chemist intuition was that if you have just a square net, isolated square net, and if you think about p orbitals on a square net, you can reason what kind of band structure you would get, rather simply by just doing the nearest neighbor hopping type binding model. You have px and py orbitals, and this is the kind of band structure you would get. So then she thought, my three-dimensional material, which has not just a square net but other elements, would resemble more of the property of two-dimensional material if the distance scale within the square net is small compared to distance to the out of the plane of the square net. It's a very sort of reasonable structural insight. And what she was surprised by was that this very simple structural insight that you can evaluate using just the known structural atomic distances was getting her pretty far when the label for the topological semimetal was based on full-blown band structure calculation. So here we have two types of materials labeled, classified, topological semimetal and trivial, depending on whether what the band structure looks like and when the band structure was calculated, either from high throughput or more detailed calculation. And the point was that if you say I'm going to look at this ratio, what they call T ratio, you get roughly a good picture. Now at this point, whether you say below the dashed line is mostly topological semimetal, above the dashed line is mostly trivial, or you say, well, there's all this misbehaving material examples, that now becomes subjective. But given how simple this is, this was pretty exciting, at least to Leslie and her collaborators, because this is a easy, very cheap quantity to go after. So what we thought we will do is we set up a machine learning architecture, supervised learning, but it is probabilistic learning, so that we can interpret what it is learning. This is the machinery. So we use the Gaussian processes regression, which is a probabilistic learning formalism, and we give this classification test. So what we did was we had about 800 materials that were tabulated, and we used all our data. So this is not having some large volume of data to train a model so that you try to predict more. Because the amount of data we had was only 800, we couldn't try to do the typical neural network-based supervised model modality. But instead, what we did was we used all the data we have to train the model to capture that the distribution in the data in the form of this correlation matrix. This is a kernel-based learning, and you learn this correlation matrix. Once we have this correlation matrix, we can figure out in the space of features that we are working with in using to represent the material, what are the features that become important together, and what are the features that are important by itself. So if my features included the atomistic distances, we would be interested in seeing whether those atomistic distances show up as an important feature in understanding the distribution of data given the labels. So what are the features that we worked with to featureize each material? The label was obtained from band structure calculations, but these feature data was based on experimental data, because most of these are atomistic properties that you can just look up in the table, the handbook. So these are electron affinity, negativity. These are atomistic properties, valence electrons. These are all properties of individual atoms. Now, my compound has multiple atoms. So what we did in this first pass through the problem was to choose the largest value among the atoms in the material and the smallest value among the elements. And because square net materials were this was organized around square net, we always make sure we include the square net atoms. So in total, we have 12 different features representing each material. And so this is what the table curated by Leslie and her collaborator, her group members look like. So this is a material, and these are the labels, whether it is square net, topological semi-metal or not. These labels were obtained by visual inspection of the band structure spaghetti plots. And these are different features, which atoms are involved, and the atomistic features. So how did it work? So question? Yes? They are all the square net families. Yeah, this was all square net families. So what we did was we first did all this with just the square net families. And so for square net families, we had this T-ratio intuition that Leslie already had. And then later we became a little more adventurous, and we tried model that was trained using square net, using that model to look at data that was not in the training set and not in the square net family. We also looked at a different material group, and we learned something that was actually useful, we believe. So that would be the transfer learning that I hope to get to. So what came out? What first came out is that, so here are our 12-dimensional feature describing a material. Now, if you think about this, how do you think about a material? Let's say something simple like NaCl. You all know what NaCl is. You can say NaCl is salt. You can say it is salty. You can say it has a cubic structure. It's white. You use the letters Na and Cl to represent it. There are many ways to think about a material. So the effort that we went through that was sort of adventurous and nobody had done before in this way was to think of like, how do we featureize a material in a way that is meaningful? And this is ad hoc, I have to admit. But we were trying to make sure we cover what seemed reasonably, we had intuition to view important, meaning all the atomistic properties that chemists typically think about were included. And we wanted to make sure that machines given a chance to discover Leslie's intuition about this T ratio, we didn't tell it to look for it. We didn't give the T ratio. We just gave those atomic distances, DSQ and DNN. And then this is the result of learning. So this is what I mean by interpreting the supervised learning result. This model, because it is a probabilistic learning within a framework, it allows us to interpret what it has learned. So here, this red dark means these correlation matrices were large, meaning it said the model thought that it has to, if it wants DSQ to be large, it wants DNN to be small. So this matrix being negative and very strong is exactly reproducing what Leslie thought to be an important feature. That's a structural feature. The ratio between, her T ratio was the ratio between DSQ and DNN. And in our model's learning framework, it is coming out to be a negative correlation matrix. But that's not the only matrix element that are highlighted. You see there's another matrix element. There are a couple other matrix elements that are highlighted. So if you look at just the ones that are coming out to be very strong, so here we're not trying to learn what is singularly important by itself. We're trying to learn correlation between different feature vectors, which is why we needed to do something like Gaussian processes, which is more expensive. And something that coming out to be interesting here is, where is it? Chi-SQ. So this is electronegativity. It says electronegativity is another feature that is important to think together with the structural property. DSQ is the distance between atoms in the square net. FCC is another way to think about the size of an atom by saying, what if my element forms an FCC lattice? What would be the lattice constant? So the way to featurize the size of the atom. So both of these are saying that I want to think about the size of the atom in the square net compound in a way that is negatively correlated with electronegativity. So this was something that got my chemist friends excited because they felt like they got vindicated. This was what got them even more excited because they felt like, wow, that was something that we didn't know to articulate. What is this? Well, this electronegativity, if we plot how we should look at the collection of materials, the whole database from the perspective of now new feature of electronegativity multiplied by FCC, the size of the atom, what we find is that the topological semimetals were kind of bounded in this middle range where electronegativity is not too large and not too small. So large electronegativity would be putting the material in a very much ionic bonding limit. Very small would be very covalent limit. And when I showed this plot to Leslie, she said, oh, that is kind of confirming something that we were often wondering about. That is hypervalency or sort of intermediate degree of covalency puts the material somewhere between ionic and covalent, which is where semi-metal is. Now, using these new feature of electronegativity in addition to T ratio, now we can separate the topological semi-metal nicely from the trivial material. And having this new atomistic feature that's not the property of the structure meant that we can use this atomistic feature to color the periodic table. The periodic table that I had difficulty learning by heart as a high school student, now I got to say, hey, I got to color this. So here we are coloring this periodic table based on our new feature, electronegativity, Chi-SQ times FCC. And we know sort of this intermediate range is where it is optimal. And those are the elements here. And that's giving us hint that you want to think about square net materials with elements involving that region of the periodic table. Actually, I don't think I have the slide that I promised to Andre, so I'll have to get back to you later. But we actually looked at the 3D cubic lattices, and we found when we use the same model, but for the 3D cubic lattice, there is no square net, so there was no T ratio. So there is only the new feature that we learned to work with, and that was giving us indication for the class of materials that have, I forgot the different name, but it was something that is like reasonably viewed as transfer learning working. So that was kind of a confirmation of what the whole procedure. Yes?
So when you try to transfer learning procedure, so you don't necessarily have like do that like you will not buy a CD, right?
Do I not?
I have a different number of data points.
Sorry. So these atomistic properties are known for elements. Those are tabulated for elements, measured and tabulated for elements. So we know those atomistic properties for every element in the periodic table.
I guess my question is like, maybe this is me misunderstanding something. It's like, if I don't have a square net,
yeah.
Elements do I take?
Right, that's a great question. Yes, that's a very good question. Right, so what you, acute observer would have noticed that the compound that I was giving all these balls drawn for had many different types of balls, not just square net and maybe one more. So then how do you, if you're going to use sort of atomistic properties and you have multiple different types of elements, how do you choose which elements to use? And if you don't have square net and if you don't know which one to be favoring to be important, how do you go about turning that material into feature, right? So that's something that we started to think much more seriously in the ongoing work. And so that I want to move over to the ongoing work where we are thinking about that much more seriously. Among the various questions, critique we got with our adventure was that, you know, people would say, I'll get to it in a minute. People would say like, you know, who cares about topological semi-metal? What good are topological semi-metal? And I would say, look, this was just the first step. We needed to have something that we know how to think about, and that's what we did. So then I will get a question about, so what else are you going to do? Will you do something that is more difficult, more interesting, where there are open questions? And that's the new adventure that we are setting off to do, which is to look at superconductivity. Question? Oh, yeah, right. That feature was presented to us to be an important feature together with another feature. It's a combination of two features. Together we're predictive. That's what this correlation matrix tells us. So there is electronegativity here. And these two data points being strong and opposite sign is internally consistent. Yeah. You mean this table? So this is not a plot of electronegativity. It is a plot of electronegativity multiplied with FCC. That's why what we found is a new feature that was, you know, cooked out, right? So it's not saying large electronegativity is good or small electronegativity is good, but it is saying you want to, what you want to optimize. So this is a coloring of our new emergent feature. That's the product of electronegativity and FCC. And we found this green region to be the optimal region. Okay? All right, so on to the new adventure, the superconductivity. So I have been long scared of superconductivity because I felt like I really don't understand it. And so I try to avoid working on superconductivity because I was scared of it. But then this whole new opportunity came up with the database of all the superconductors. So this supercon database curated by Japanese material science superconductivity research community has 30,000 plus entries, and it's covering 16,000 plus materials. Now, you notice that the numbers are not matching, which means a given material has multiple entries. And why is that? The reason is because they have collected all the papers. So here is an example of one paper reporting something about MGB2, another paper reporting something about MGB2. So these 30,000 entries are papers. There are 30,000 papers they have collected. And they went through all those papers and tabulated properties that are reported in each of the papers. These are measured properties. Now, when you make a database like this, it's not going to have a nice rectangular shape. What I mean is that, first of all, different materials are studied different number of times. And also, different research groups would decide to measure different things. So the only thing that is reported for every single material in the database, obviously, is TC, because it's a database of superconductors. But there are other things that are reported as well. And we started to think that maybe we want to extend the lessons that we've learned from studying the topological semimetal to the study of this database. And this adventure is, once again, the person who's bearing large part of the burden is my student Yanjun Liu, former postdoc Krishna, and Omri, who is actually here, has recently joined the effort. And he is much more of an expert in details of how things work. But because this is an ongoing work, I'm not going to be able to give you actual details of what we're doing, but I want to just kind of give you a picture of how we are approaching this. So the database, there are two types of data in this database. And often people thought of this as, well, we would like the data to have a nice rectangular table structure. Because if you have a table, you can stuff the table into a machinery. So removing all the redundancies, if MGB2 shows up 196 times, compress that into one, because this standardized data wants one entry per material. And keeping only what is reported everywhere, which will be TC. Everybody, the community wanted to know the structure, the role of structure. So this 3DSC was an effort that was led by actually previous lecturer Jorg and his colleagues, sort of reducing the supercon database into something that takes a rectangular form and adding to it the structural information. So in this database, there's TC, chemical formula, and CIF files of structure, whether it is sourced from materials project or ICSD. There's another additional information in the supercon database, that's the literature. There are all these papers, 30,000 papers associated with all the superconductors that are known to these researchers. So what are the efforts that have been going on? There have been focus to the standardized data, that is the TC, chemical formula, and the structure sometimes. And coming back to the earlier question, if you have multiple elements in the material and you want to think about the chemistry, how do you featurize? Often people use something like average electronegativity. You've got 6 different elements. You're going to use average of the electronegativity of all 6 elements to describe the material. And we believe that is that there may be a better way to do this. So this is sort of what the landscape until now looks like. And our effort is to try to look at the structure from structure and the chemical information simultaneously by looking at the structure as through a graph-lit expansions. And we're looking at the information, structural information from ICSD as well as materials project. Now, I cannot go into the details of how we are featurizing, how does our graph-lit expansion actually work. But here is just some preliminary results where it shows that including higher order graphlets give us improved predictability. So what we're doing here is we use some fraction of the data to train the model, and then with the TC. So here, instead of binary classification, we're training the model with the TC and the information that we have featurized. And this R square score in the ideal limit should be 1. It shows how much of the real data we are capturing correctly. And what you can see here is that the R2 score improves when we especially go from first order graphlet to second order graphlet, and especially compared to the earlier featurization using average of atomistic properties. This gap between training R square and the test R square is saying that there is some overfitting going on, and this is a preliminary result that we are working to improve upon. But it's something that gave us enough encouragement that this approach, our way of principled featurization, has a potential of yielding. Another thing that we are getting by using our methodology that we developed from the earlier work on topological semi-metal is that we have interpretability. Because we have interpretability, we can say which are the features that are being responsible for the predictions. So these are different features that are being responsible for about 70% of the total learned weight. And what we're finding is that atomic weight is important. That kind of makes sense. And there are a bunch of other properties that we haven't yet had chance to think deeply about. But this is sort of a direction where our effort is moving on to. Now, before I switch gear, question, Andre? Yes. Omri, this preliminary, where are you, Omri? Yes, this preliminary result, what was it just a low TC one? Yeah, so this was just a low TC one. Yeah. Yes? You have to ask Omri privately. I cannot broadcast this. This is being recorded, right? Yes? Right, their TC would be 0. That would be predicting correctly. Yes. But there are some secrets that I'm not revealing. It's not perfect right now. A lot of work to do. Yes? Oh, these are, so because I am not showing you what the graphlets are, these don't necessarily make sense. But what this graphlet is a way of, you have atomic structure, which means you have these balls arranged in a particular way. So you think of the arrangement of the atoms, the identity of the element is chemistry, location of the atoms with respect to each other is structure. You can think of that as collection of graphlets that are increasing degree of extendedness. So if I think about all the properties associated with the atom itself, that's 0th order. If I think about, that's the 1st order. If I think about what are different ways of 2 atoms being next to each other, those are 2nd order. So those would be bonds. So bonding information will be incorporated. So 3rd order will be like 3 atom arrangement. Yeah. So when we look at these features, we're including the chemical information and structural information together. All right. So now I'm going to switch gears and talk about a different approach. So the first part of the lecture was about where we write the machine learning architecture. Often we're not writing from scratch. We are heavily using the community developed packages. There are a lot of packages in like scikit-learn, PyTorch, what's called gPyTorch. My collaborators have developed. This is the GP in the PyTorch language. So there are all these packages and the libraries, and we're using them heavily, but we are kind of pulling them together to build the architecture. Now, in the second part of the talk, I want to talk about using the large language models or the tools that are driven with large language models as engine. Large language models it's a collective way of describing ChatGPT, Gemini, Perplexity, all of those. Those are all language models that are pre-trained. ChatGPT first made the splash before ChatGPT. Google also had a large language model that they were not comfortable revealing because it wasn't perfect. ChatGPT came out with something that was hallucinating nevertheless. But these are all pre-trained models. So what it means is that you take a large corpus of language data, lots of papers. For instance, you can download every single paper on the archive. It's been actually already downloaded and turned into a database. You can just take that. It's not huge because it's LaTeX. Most of it is LaTeX. So people have trained these language models with large corpus of documents. And now we are wondering, what can we do with these language models going beyond generating weird pictures that my daughter likes to do? So what is the landscape? This is already old. This slide was made last year. You can see like 2022 our archive. What made a big splash this year was beating the International Math Olympiad IMO problems. But generally, people have started using these language models in medicine, in chemistry, and a lot has been done in testing their abilities against undergraduate math, science textbook problems. So what's common to most of these approaches are what you're asking these models to do is sort of one response type of question. Here's an example. Question, line parallel to ... what is the y coordinate? Asking them to solve a question that would have a short answer. Maybe long answer, but one sentence. These are not asking these models to do some sort of a reasoning task. And what we started asking was, can we use large language models for research problems that require multiple steps of reasoning? And what we picked as a target sort of problem to study was the Hartree-Fock mean field theory. So this is the paper, and you can find details in this preprint. It's going to appear in communication physics very soon. And it was really led by Haining Tan, who was a postdoc in my group, who's later moved to Rutgers. So why Hartree-Fock? If you look at because you can just download the entire archive, you can start hashing out how many of the papers in the archive from this year to this year have Hartree-Fock mean field theory in it, right? So these are all the papers in the archive from this point in time to this point in time. These are the number under CondMet. These are the papers that mention Hartree-Fock or mean field in the abstract. We've excluded bosons and superconductivity. We excluded various spin liquid type mean field theories. And we also excluded more sophisticated and complicated work, algorithms or approaches combined with mean field theory, such as DMFT, ED, etc. And that gave us, about 4,000 papers, which means this is something that is done a lot. So how do we go about trying to turn something that we all know is very formulaic? Some of us do Hartree-Fock more than others, but we all know it is a well-structured, very formulaic approach. Yes, Andre? So we only right. So Hartree-Fock also means different things. You can do like Hartree-Fock like chemist, right? And that is very much of a brute force, right? Because there's the Hamiltonian. That's not what we did. We are not looking at those. And so what we did here was very much like what condensed people do, coming up with some model, and then you try to do a mean field decomposition. So the procedure of, so now something that you can, the hat that I wore when we were working on this is imagining some, I don't know, senior undergrad or first year graduate student knock at your door and say, I want to do research in your group. I want to try a research project. And you ask them, what do you know? And the student says, I know how to do LaTeX. I know second quantization. I know what lattice looks like and what Fourier transform is. Can you give me something to do? And depending on the degree of sophistication of the student, if it is a experienced student, let's say, I don't know, couple years on in the graduate school, you will say, well, let's think about pentalayer graphene, which can have potentially some quantum Hall crystals and this and that other things. Why don't you go do Hartree-Fock mean field theory and come back to me with a phase diagram? Think about 3 different parameters as the parameter in your Hamiltonian. It took me what, a minute, right? If you are a kinder advisor, you might even give you a statement that amounts to an abstract. Now, a student who can go off with it and come back to you with a reliable phase diagram in, I don't know, a week or 2 would be someone who is already, very much advanced. But going back to my first year graduate student or undergrad who does not have that experience, you cannot just do what I just said, right? So if you have a student who needs much more guidance because this is their very first time doing Hartree-Fock mean field theory, you would have to break it down. You will have to tell them, okay, here's Hamiltonian. Now you have to first do mean field decoupling and arrive at the mean field Hamiltonian. And then you have to solve that mean field Hamiltonian self-consistently. Once you have a working code that can solve that mean field Hamiltonian consistently, then what you have to do is to explore the phase space of parameters. And remember, when you try to explore the phase space of parameters, sometimes you'll get stuck in the local minima. And because you're a first year student, you don't have an experience, I will walk you through. So why don't you go first, come back to me with a mean field Hamiltonian? You might do that, right? So that's what we did. But in order to give this in order to be not like my mother, who told me to use right amount of this and right amount of that, but to be a kind recipe giving, I don't know, person, we need to break down. And this is something that I find really interesting working with computers. Computers are honest. They don't make up stuff that if they don't know to make up stuff if you don't kind of figure out, if you don't tell them a well-defined instruction. Or actually large language models make up stuff, but you don't want them to make up stuff. So in order to avoid hallucination and arrive at something reliable, you have to formulate everything in a nice structure. So what we thought of deriving the mean field Hamiltonian, Hartree-Fock mean field Hamiltonian, as a whole bunch of steps. You have to first write down your Hamiltonian, non-interacting term and interacting term. And often you would have to do the Fourier transform because kinetic energy is easier in the Fourier space. So you have to go through the Fourier transform. And then you have to apply Wick's theorem to do the mean field decoupling. And maybe there are some constant terms that you have to drop. And you have to make sure you're satisfying momentum conservation. You separate the Hartree term and the Fock term. And you recognize what is the order parameter in the Hartree term, what is the order parameter in the Fock term. You express them with your expectation values. And then you will arrive at a Hartree-Fock mean field Hamiltonian. So the question we asked was, can large language model do this? So we did this experiment by trying to reproduce 15 different papers. You know, from 4,000 to 15 is a humongous amount of reduction. But we kind of started excluding different things but most importantly, we needed to be able to give the ground truth. So we kind of limited ourselves to a selection of papers, which we'll show you in a bit. But generally, the framework that we worked out, and this was kind of interesting because, you know, some people said, well, Eun-Ah, that's not physics. But other people later, I'm increasingly hearing from people that, you know, I'm reading that paper and, you know, we're trying to mimic what you've done. So what is it that we've done? We didn't invent ChatGPT. I have no connections to ChatGPT, so that's not what I did. But what we did do is to figure out how do we make this work for us, right? So what we thought, you know, if in order to apply a framework that is very formulaic across different problems, we thought of writing a prompt template. So this is our prompt template, where there are placeholders which can be replaced by problem-specific information so that we have the fixed template, and to fixed template, we plug in the placeholder associated with a given problem, and we give that to the large language model. We try Gemini and ChatGPT, and it will give us the Hartree-Fock Hamiltonian. We also tried to see if it can be lazier, or the painful part of this approach was figuring out all those information to be plugged in. So we thought to see how much of the information that we need in order to carry this calculation through step by step can be inferred or extracted just from the abstract. So this is an abstract. Now, whether you can infer how much of the information that you need from the abstract is not just a function of the large language model capabilities. It also depends on how well the abstract was written. But if the abstract was well written, it should state what problem it's studying and what are the orders that were considered. So we tried to see if we can use a language model to extract the information we need to run this experiment from the abstract. And that was also possible. So here is an example of trying to extract information from abstract. This is a screenshot. Here is the prompt. Prompts are long because that's how we make sure it does the right thing. So now I give this long prompt and give an example of what a corrected response from a given abstract example would look like. And ChatGPT says, I understand the instructions. Please go ahead and point your questions regarding the abstract. So here, I gave the abstract, and it quotes part of the abstract that it is using to extract information. It gives the explanation for how it reasoned and gives the answer. And then I can keep asking these questions that I need in order to fill the placeholders. So this is an example of one of the papers that were in our 15 paper samples. It says, based on this phrase, AB stack ditelluride tungsten diselenide, it reasoned that energy dispersion of the kinetic term should be parabolic. Not bad. It can say this because it has read a ton of papers on TME. So this is an example of what executed outcome looks like. ChatGPT gave us all LaTeX codes. So these are, you take the output and put it through a LaTeX engine, and you get these nice equations. I said my student knew how to LaTeX, and indeed, this student knew how to LaTeX. So these are the papers that we looked at. 5 or 6 of them are Heining's papers. We got into this because Heining had done a lot of Hartree-Fock calculations. So that meant we knew what the ground truth is, which allowed us to make various evaluations. So these are the steps of analytic derivation. We had turned the whole exercise into 11-step process. Each output has to go into the next step, and this is what we went through. Now I'm running out of time, so I'm just going to show you what the output, how well it did. What was kind of interesting was reading turned out to be a harder task. Trying to read from the abstract, that is, not the paper. Trying to infer from the abstract a specific information could be a challenging task. But if we give examples of what's the right thing to do, that's called one-shot. The performance improved tremendously. What was really cute was how good GPT-4, this is now old model, was at applying Wick's theorem, like almost perfect. You know, in actual mechanical part of doing the mean field decomposition, it did really well. So we have these statistics we reported in this paper. Interestingly, these were the papers that were written or posted. So we worked with GPT-4 at the time. It had a timestamp. It was trained with papers up to this point, up to September of 2021. And these papers were officially not part of its training data. Moreover, these mean field equations were often not in the papers anyway. So this was these were the performances. Now, after we did this work and I went around talking to friends, and my friends started to tell me that, well, you know, it's nice that you can derive, but it would be really nice if it can code. And, you know, and then my friends will sheepishly confess that they cannot code. So it would be nice if a computer can code for them. So that's the next adventure that we embarked on too. Now for this, I'm going to spend a couple of minutes and do a live demo because it was really exciting. One of the people who cannot code is me. So for me to produce 9 codes in one weekend morning was kind of exciting. So here, okay, so let's see. Here's my GPT asking me how it can help. And here is, this is the prompt. It's long. This prompt, so we need to use a model that can handle large context window. Prompt has placeholders where the functions that we wrote to do Hartree-Fock, we wrote there's a couple of useful functions, goes in. And then there's a place for where the Hamiltonian, mean field Hamiltonian goes, and the lattice symmetry goes. Lattice symmetry information is necessary to do the Fourier transform correctly. So I'm going to copy this in to my chat window. Now I have to specify information like the functions that we wrote. So these are, we have the Hartree-Fock Hamiltonian is defined, what it means to generate the non-interacting term, interacting term. We define these things as predefined functions. So I'm going to copy those in the place of docstring. And now I have to give the Hamiltonian that I want to look at. So these are mean field Hamiltonians for our 11 papers that we looked at. I'm going to pick this one. So I place that in the Hamiltonian part. The prompt is written so that it would not just spit out the code, but it would answer a bunch of questions so that we can see that it is thinking along the right line. And the symmetry for this model, this problem was square. So I will specify that. Now I'm going to run. Now it's thinking. Piecing together Hamiltonian elements. It's kind of telling you what it's doing as it does stuff. Pulling together spin and orbital flavors. It tends to take about 1.5 minutes to 2 minutes to arrive at the code. It's almost done. Yeah. No, it wasn't constructed to inform those steps. It's telling us what it is doing. That's how O1 model works. So it does reasoning, and it takes time to reason. And while it's reasoning, it tells you what it is thinking through. And now it's giving us answers to the questions. We structured our prompt so that it would first answer a bunch of questions. And looking at these answers help us see whether this code is doing the right thing, because we would recognize these answers. So these are different dispersions and different interaction terms. And now here's the code. This is a Python code. It has written. It's still typing. And notice how nicely commented the code is, because it's trained with nicely commented codes. So when I get this code, I can look at it and actually understand what is going on, because it is very clearly commented. And it would even, in the comments, include like what would be a different way to do something. Yeah? Yes. Yes. Right. Mm-hmm. 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 Right, right, right. So there's a timestamp, right? So when we say we've done something, we would specify which model with which timestamp, right? So it is not. It's kind of like, what was it? Device 1 versus device 2 versus device 250. Device 250, when it becomes public, probably is better than device 1 and 2, as we heard yesterday. And what you've seen in device 1, some of it might be artifact, and some of it might have a standing chance. So what we are producing is here, what we are interested in doing is not so much the output of the model. That's not our what we are producing. That's not the product that we're putting out. What we are putting out is, in a way, what I did not detail. That is the prompt, that structure of the prompt. It was a year of effort that went into figuring out how to make this work, right? And we structured the prompt so that the code would come out executable. And while we were first doing this with GPT-4, it didn't work, and various other models, it wasn't working. But O1 made a big difference. It was a really big difference between O1 and all the other models that we looked at. And so while we were getting to the point of, okay, we've got code, but the darn thing is not running, and then we started using O1, and now it's running. And now we can ask the next question. How do you know if these codes are right? Now, the answers to questions that we designed it to answer the questions for two reasons. It gives us something to look at to evaluate, but also when these language models answer these questions, they tend to be more correct. They are more grounded when they are forced to answer questions. They think along the right way. And it's a little bit like, when you talk to a student or somebody that you're trying to guide, you ask them questions. You try to make sure that their thinking process is going along the right path. And making it go through answering is helpful for its performance, but it's also helpful for us. But ultimately, for us to evaluate whether these codes are right, we need some way of assessing it, that is not reading line by line. So then that's something that we are working on developing. And as we start to think about if I have 15 codes that are all running, how do I check whether those codes are right when we don't have other codes to compare to? But even if I had other codes to compare to, you cannot compare a bunch of codes to another one, especially one of them is not well commented, right? So we started to think about like, okay, so you're an advisor and you didn't write the code, and your student comes back to me and says, he or she has done the calculation. How do you know they are right? If you're going to put your name on it, you got to make sure it is right. So how do you make sure they are right? You're not going to do that by reading line by line of the code. You ask prodding questions to see whether the answers make sense. And that's the process that we are figuring out. We are figuring out, given the code, so we are developing a notebook where you load in the code and you run the code, the notebook will run the code, and it would give in different limits. For instance, if you're doing Hartree-Fock, you would have non-interacting limit and you would have strong interacting limit, and those two limits are always well known. So you run the code and make it solve the questions, the equations in those limits, and you look at the answers. That's one way. And there are and so this is something that is ongoing. And what we are doing here is actually part of the larger world's effort in what's called agentic workflow. So I think maybe Google claimed that year 2025 is going to be the year of agents, meaning these models are like, secretary or graduate student or somebody who's doing repetitive and well-defined tasks. So figuring out how to make these agents do what would be painful for you to do, what could be accelerated, what could be automated, there's a lot of effort going in figuring out how to use these models to as a useful agent and helpers. And what we are doing in this research is figuring out that for sort of physics theory research. Another thing that we are figuring out as we try to we divided the task of generating 15 codes among 3 people. Each wrote like 5 codes, and we've got all of them. Now, what do we do with them? And as we try to think about how do we check whether they're right, and then see whether we can just explore the phase space with each one of them, we ran into the next question of, well, anybody who do numerics, especially those students who are carrying from the why don't you solve this mean field equation command to the result, spend an awful lot of time babysitting the calculation. Your simulation may get stuck somewhere, or you thought you let it run and you thought you can just go away and have nice lunch and come back, the results should be waiting for you. Instead, you come back from lunch, you find that it ran out of memory and didn't go anywhere. Like all these painful instances which make you sit there and babysit your calculation limit, it's not only the compute time that limits how limited scope of 8-dimensional, 10-dimensional space that you can explore. It's the human time that is required to do this babysitting. And babysitting numerical simulation is something that happens across the board, not just in many-body physics. So how to use these agents to make right judgment calls as you would make as a person sitting in front of the computer to carry out, babysit the carrying out of the calculations. So these models are not, it's not their job to run, to be the simulator. Their job is to manage stuff. They can pull in the codes, they can pull in tools, they can pull in packages, and they can manage, distribute, and pull things in, push things out, sort of manager, secretary. And so that's direction that is interesting from our point of view. When I think about these as efforts, so I kind of feel like senior researchers have the moral obligation to educate our students and postdocs, our next generation, to spend as much time and effort growing as thinkers, not doing manual labors. So anything that is manual and repetitive should be automatable and will be automated. And that's sort of what we are trying to figure out, how to make more of our time spent in thinking and less doing labor. Yes?
So I guess my question is more in terms of like, okay, so you put out the scenario where you have like professor who knows like a bunch of stuff before, like they have a bunch of insight. They've probably coded a Hartree-Fock simulation before, right?
I have never done it.
You have never done
Yeah,
it?
this was my first time.
That's
I mean, I've never done it. I've written papers, but I didn't code one myself.
But still, like there's like this base of insight that you have developed regardless from your interactions with other people. So imagine like a first year grad student and my second year as well.
Yeah.
And like I know how to code a Hartree-Fock simulation, but I'm imagining like me 2 years ago, where I just go to ChatGPT and then I try and get to, so that I'm just saying there's like, is there like some fear that like instead of learning how, so you need like a fair amount of insight to get it right, right? So is there like some
That's a good question. Yeah, that's a fair question. So why do you think I've never coded one before?
Someone else did it?
No, just because I don't know how to code. So the question is, for me to code before, I had to learn some syntax, and I never got beyond hello world when I was trying to learn C. And then world moved on to C++ and Python and whatnot. I mean, I can use Mathematica. That's as far as I can get. What these models do very well is translation. So your natural language can be translated into code. You can ask it to write in Julia. You can ask it to write in Python. You can give it a Python code. It will turn into Julia, because these translate. So the burden of syntax can be lowered now. We don't need to be tied down by syntax. You miss some semicolon somewhere and your code will not run. That kind of like that's not, it's that kind of burden that we become free of. But there is a fair question of when young ones learn to just be lazy and do everything with ChatGPT, are they learning anything? So let me just answer this. I know I'm over time. I think it depends on how you use it and whether you have a desire to learn. I taught several courses, often when I teach a course for the first time, I often think I'm the one who's learning the best. If there is A+++++, I should be getting that because compared to everybody else, I am really learning because I'm trying to teach, right? So trying to teach somebody is a very good learning experience. So if you try to teach ChatGPT, you all get to have a underling now. You can try to teach this underling to do the right thing. And in the process of trying to make the underling do the right thing, you will learn what are the important things that should not be missed, right? So and you can go through repetition at a faster rate. So by repeating multiple different types of problems, you kind of gain that intuition. Intuition is something that we gain through experience. Maybe our brain is preconditioned to be able to connect and build a network that will do intelligent and amazing things. But we also know of stories of some poor kid who was raised by wolves and discovered at age 13 and can never learn to speak because didn't get that critical experience at the age when the learning was supposed to happen. So we learn through experiences, and I think of these things as giving us experiences. Now, coming back to, is it okay to not know how things work? Now, how many of you calculated, let's say, associated Legendre polynomial by hand with paper and pencil only? Not using computer anywhere. Do you even remember what that thing is? I know because I just taught it. Okay, now you would probably, if you have to plot, you would pull out Mathematica Python or something, and you call the function, and you'll call plotting function and plot it. Do you know how that machine plots that? You know that it makes approximations. You know it terminates, and it's only accurate to the machine precision. We don't think about it because we don't look inside of how it does, right? And why is that okay? It probably wouldn't. Maybe it would have been really blasphemous to those who wrote those books, a long time ago. And those books are still very important because we need to somehow know how things are working. Knowing how things are working, that knowledge is really important. But being able to get to answers quickly, reducing labor, instead of using slide rule to calculate logs, or looking through piles of power of table of logarithms to calculate log, when you can just ask, hey Siri, what is the log of 27, and get an answer. Maybe one of your series are going to try to do that. It allows it gives you time to do other things, right? So I think these are tools, and it's not going to go away no matter how much you fear them. And it's how much you make use of it and how you use it and how you learn. I think it's ultimately responsibility come back to you. You guys are not learning because you're trying to get A+ in a course. You're learning because you are inherently curious. You want to know the answer. You want to learn. You want to learn the process. So how you use it to aid your learning is up to you. Yes. We are way over time, and there is a Q&A session, right? Yeah. So let's postpone. Yeah.